Good morning, good evening, wherever you are. My name is Rich McFadden, and thank you for joining our webinar, Understanding the Basics of Digital Multimeter Calibration. While we were getting set up here, we did run a poll, and it looks like we are spread out all over the world, actually. We've got a few as far as India, South America, and it looks like a good spread across the United States here. So thank you for filling that out. We're really excited to bring this webinar to you. And this is part of a series that we're going to be running over the next 6 months, really focused on getting back to the basics. Today, we will be focused on digital multimeter calibration, and I'm with Wally Miller. He will do an introduction in just a moment. I want to do one thing before we get started, just to help Wally. And I've got a poll here to gauge your experience level with calibration. You don't have to answer this, but what it'll allow us to do is understand the audience's experience so that we can tailor our messaging. So I just popped that poll up there. Excellent, thank you for filling that out. Wow, looks like we got a good span here, Wally. So a good mix of some veterans in the group, some that are new to calibration, and some that have never calibrated a DMM before. So thank you for those answers. So let's go ahead and get started now. So Wally, why don't you go ahead and get kicked off and introduce yourself?
Sure. So as Rich alluded to, I'm Wally Miller. I'm a product program manager here at Fluke. And I've been within the company for a long time, 35 or so odd years. Started out in engineering, progressed from marketing to sales, sales management, and now I'm back into product management again. Educationally, I've got a BS in electrical engineering and then an MBA, both from the University of Washington here in Seattle. So I've had a bit of experience around the world and with calibration and metrology, which is the science of measurements. A couple things here. I think you probably guys, most of us who have been in the pandemic for the last year or so, understand some of the webinar etiquette, which is, we're doing this via over IP. We've got a Q&A session, and you can go and throw those things into the chat. If you have questions, I really do encourage questions. To kind of help me stay on track and make certain that this presentation is the most beneficial to you by getting your questions answered. There are a couple of places in the session where we will take breaks and opportunities to discuss things and probably address some of those questions that have come up. The copies of the presentation and the recording of the session will be available to all people who registered, and an email will follow up shortly after, within a day or so. It takes about, well, it used to take about 24 hours to get the recording in a state where we can actually publish it. So we're going to go back and look at the basics here. A lot of this is, really just understanding, a little bit about what the technology is and what we do. So objectives for the day or for this next hour or so is to give you a little bit of an understanding of the technology of a DMM. We're going to talk about selecting the proper calibrator, looking at some general practices for calibrating digital multimeters, go through some examples and recommendations for quality calibration. And throughout the presentation, we've spattered in some technical references, and we'll have all of those with links to those in the presentation as well. So I start out with, talking about a digital multimeter. It's probably the most commonly used piece of electrical test instrumentation, and it's used a lot in troubleshooting, but also a lot of quality processes depend on its proper use and its proper operation. A lot of people will use a DMM to adjust their process, and they can only adjust it as well as the meter can actually make quality measurements. One of the things that we talk about in metrology is that all instruments, they change over time, their characteristics. You can see that from environmental conditions causing change, sometimes physical use, heating, overheating, cooling it off, and even just physical shock, vibration, abuse will change what a measurement device does. And the real question is, how do you manage working with these changes? So if your measurement device is changing, how do you know when you've seen a change in your process, whether that's the device that's changed that you're making the measurement, or truly a change in the process? So that's really what we're looking at here. And regular calibration is really just the way that you confirm that your DMM continues to test and measure properly within specification. It is a part of a quality system. Without periodic calibration and verification, most people would say that you don't have a quality system. So it is an essential part of maintaining product quality. A lot of people will say, well, okay, that's good and dandy, fine. Can you give me a little bit more information about why you would calibrate test equipment? So we have an app note that we published a few years ago that provides answers in much more detail about why you'd calibrate test equipment. And that's available from one of our websites. So if we look at DMMs, I tend to classify DMMs in 3 different categories. Now I'm showing you Fluke versions of these different categories. There are certainly other manufacturers that have meters or digital multimeters that fit in these categories as well. They start out with, on the left over here, with a handheld DMM, a little bit more accurate, a little bit more, just looking at the number of digits on display, you can see there's certainly more resolution with getting into bench and system DMMs. And then the most accurate tend to be these large laboratory DMMs. And that's part of how I classify them by performance. A lot of people will classify them by the number of digits, like the handheld, the 179 there is a 4.5 digit DMM. The bench DMM is a 6.5 digit, and the one on the top is 8.5. The number of digits tends to coincide with its accuracy and its performance, but not always. So handheld DMMs, they're easily the most versatile, but they're the least accurate. Generally, you see these things at 3.5, 4.5 digits of resolution. They have the same basic 5 features. When I say 5 features, I'm talking AC volts, DC volts, AC current, DC current, and amps, or ohms, sorry. So you've got volts, AC, DC, amps, AC, DC, and ohms. But a lot of the more modern handhelds are also including other functions and other measurement capabilities that are quite useful for frequency, continuity, diode testing, peak holds, temperature, capacitance. Some are actually even giving you some waveform information. When we get to systems or bench DMMs, they're considerably more accurate generally than a handheld. These tend to fall in the range of 4.5 to 6.5 digits. They have the same basic 5 functions, although I tend to find from a measurement standpoint, bench DMMs tend to have fewer secondary functions beyond the volts, amps, and ohms. But what they do is they drill into each of those 5 functions and provide a variety of different ways of measuring them. For example, we may find different modes of resistance measurements, 2-wire, 4-wire, things like that. These devices are generally, or have the capability of being configured for remote operation. And depending on the model, today, almost all of these are software calibrated and can be done in a fully automated manner. The bench DMMs, these are, as I said, the most accurate. They're generally, they take over where I said the laboratory instruments, they take over where the bench instruments stop at about 6.5 digits, and they go up to 8.5. And I think 8.5 is about the highest resolution that you'll find in a commercially available multimeter at this point. These devices really are much more limited in the parameters that they measure, generally just 5 functions, as I have here. And often, most of the time, these things are used in a remote fashion, much more automated in automated systems and those sorts of things. When I start talking about each of these devices and we get into the calibration, it's really important to understand how to apply, what the specifications of a DMM are. The calibration process really is confirming the digital multimeter's performance relative to its required specifications. So a lot of times you can use the standard that you're comparing these things against can be the manufacturer's spec, or sometimes it can be a custom spec. Sometimes there may be a time where we use these devices to something better than their published specifications, or sometimes they're worse than their published specifications, or sometimes it may even be a limited subset of their functionality. I'm only using the meter in current mode, so why would I test any of the other functions? So that's how you need to understand where these where the specifications are and what specifications you're comparing against. When I get to specs, you'll start seeing some of the differences. So here on the left-hand side of the screen, I've got the specifications for a Fluke 179, which was that handheld, or actually all three, the 175, the 177, and the 179. And then that one simple table, I have 3 DMMs being specified. I have all of their functionalities. So I've got AC volts, DC volts, ohms, amps, all of them, all of the functionality of the meter being spec'd. That's for a simple 3.5 digit multimeter. If I look over on the right, I get one of those bench meters. I've got almost the same number, set of numbers in terms of complexity. But if you look at it, that section on the right is only looking at one function, DC volts. So as you get to a more precise meter or measurement, the number of specifications, the amount of specification generally increases to provide more specificity in how the results can be applied. If I go even one step further, now if I'm looking at an 8.5 digit multimeter, I couldn't even fit these on the same screen. And I even had to cut and paste different sections because this isn't complete. But for example, this is just the DC volt function for that 8.5 digit meter that I was showing from Fluke. And if I wanted to pull out the full spec extended specification sheet, it's 28 pages long. So what happens here, as you get more precision and accuracy, it means more spec complexity. And that's one of the challenges as you get to a more complex DMM. Understanding, if you got your meter and you're trying to choose a device, a source, because your meter is a measurement device, so you have to have a source to calibrate it. You need to take a look at the specifications of the calibrator. And generally speaking, what we want is we want the source to be at least 4 times better than the measurement device that it's calibrating. There are some exceptions to that, but generally speaking, we're looking for 4, at least 4. The more you can get, the more, if it could be 5, 6, or 10 times better, that's actually providing more confidence in your calibrations, but we suggest 4. The other thing that happens is you need to have the functions of the calibrator cover the functions of the DMM that you're calibrating. So, for a handheld DMM, you're going to need at least those 5 basic functions, plus any ancillary functions to fully calibrate the instrument. Often, the technical manual for a DMM, if you're lucky enough to buy one from a manufacturer that publishes one, they'll actually provide the recommendations for the calibration device, the functions, and the minimum specifications required. If you don't have a technical manual for the DMM that you're looking for, there are some published guidelines from recognized organizations around the world that provide recommended practices for DMM calibration. And I'll give you an example of one of those as we move on in the seminar.
Wally, a clarifying question. 4 times better, you mean accuracy?
Right. So, and we'll go and give you an example of that in a slide. But for just in stupid raw numbers, say we had something that is specified as accurate to 1%. If you're going to calibrate it, you would need a source that's accurate to 0.25%. So at least 4 times better. And what being a metrologist, I'm butchering the languages. Some of you know that accuracy is not really the right term to use. It's really uncertainty, but for basics, I think accuracy is an appropriate term to use. One of the things that you can use to help you choose a calibrator from Fluke, we have this workload matrix. It's on our website, and it provides a summary of the functions and summary accuracies for all of our calibrators. But what the interesting thing is, let me see if I can't get my pointer over here. Let's do that. So, thought I had it just a second. There we go. So, across the top up here, we have all of our calibrators. And then down this side, there are different workload parameters. So, here is different DMMs of different levels of accuracy, some temperature functions, oscilloscopes if you want to do that. If there are some other devices that you're calibrating, safety, whatever. But for examples here, say we're talking about DMMs, depending upon the accuracy and we've summarized that both in number of digits and a typical accuracy number, you can see which of these calibrators could perform a calibration. So our most accurate calibrator covers all of these, but our least accurate one probably only would do 3.5 digits. So that's how you could use this sheet to kind of zero in on the type of calibrator you're interested in, and then look at it in more detail as necessary.
Wally, we have a little spoiler alert. Well, in the next few webinars, we'll have one on understanding specifications. But there was a question that came up that says, can you give an example of calculating accuracy as a % of reading versus accuracy or % of range? I don't think we can give a written example, but can you describe the difference between those two?
You got it right here. In fact, this slide talks about it exactly. So let's just take a look at a 3.5 digit multimeter. Let's look at that Fluke 179, and let's find out what its spec is at 5 volts. So if it was measuring 5 volts, what would the spec be? And so I've highlighted here on the table. Can you see, is my cursor following around, or I need to go back?
I can see your cursor just fine. Yep.
Okay. So if you look at the DC volts, the specification is 0.09%, and it says up here, % of reading plus counts or plus counts. So what that means is it's 0.09% of the value that you're reading plus 2 times the minimum resolution or count. So here's how we do the math. At 5 volts, the meter's best range is the 6-volt range with a resolution of 1 millivolt, 0.001. So we calculate the percent of reading, so 0.09%. Remember, we're reading 5 volts. So 0.09% of 5 is 0.0045. So 4.5 millivolts. That's your percent of reading or gain portion. And then the other portion, plus or minus 2 counts, or plus or minus 2 times the resolution, or 2 millivolts. You add those together and you get a spec of 0.0065. Since the DMM can only display 3 values after the decimal point, it's a 3.5 digit meter, it would get rounded up to 0.007. So the spec or the accuracy or the error of this meter at 5 volts, measuring 5 volts, would be 7 millivolts. So that's how we would go about doing that calculation. And you can do that calculation for all of the other parameters, and they're spec'd very similarly each time. So if I'm looking to test this meter, the meter says, the specification says it's at 5 volts, it's plus or minus 7 millivolts or 0.007. So it would be in spec if it read 5.007 or as low as 4.993. Anywhere in that range would be within specification, given a perfect 5-volt signal. All right. If you happen to be lucky enough and the manufacturer of the DMM publishes a performance spec, you should be able to go look at that test or that performance test and check your work against that spec. So if you look over here, that's exactly what I've done at 5 volts, which happens to be a test point. You can see the lower limit and the upper limit, and that matches what we calculated on the previous slide. So you should always, I would say, refer to the DMM's service manual for detailed information. Manufacturer, if they're a quality manufacturer, should be providing pass or fail limits with which you can evaluate against the manufacturer's published spec. And of course, you can apply more points if you want to, or if you are operating at a different specification of accuracy, you can calibrate your own test limits or calculate your own test limits. Other things that you need to look at when we're doing a calibration. This is one of the things that people often miss, but you really should check fuses, replace them if necessary. I would say cleaning the device. A lot of the DMMs that we see coming into our facility are quite dirty, just cleaning them up. I would strongly recommend, if it's a battery operated device, replacing the battery before you do the calibration. Looking for excessive wear. Look at the terminals, and the terminals still provide a snug fit to for the test leads. Do you still have, is there anything cracked or broken? Those ideas. You will certainly want to stabilize the unit under test in the same environment that the calibrator is, and you want to make certain that the calibrator has been on and warmed up so that it is operating within its specifications as well. So routine calibration includes all of these things. What's the proper calibrator for the DMM? So as I mentioned earlier, common practices are at least 4 times better than the UUT. So if we're looking at a 7 millivolt error or spec, or 0.014% of reading, at 5 volts, the calibrator should be 4 times better. And so if I took 7 millivolts and divide it by 4, it should be at least 1.8 millivolts, or 0.14% of reading divided by 4 gives you 0.035% of reading. This needs to be done on all of the functions and all of the test points that you're going to calibrate at. You need to make certain that you've got that. For most of the Fluke meters, we do most of this work for you, and we provide in the technical service manual, we provide a required or recommended calibrator, and so it will be this 5500 multi-product calibrator or equivalent. So if you have one of those, you should be fine. If you don't have one and you've got other pieces of equipment, for each of the measurement functions, there's a minimum accuracy required. So both range and accuracy for each of those functions that is published. So if you have something better than that, great. Something not as good, then you've got to do some additional work. Rich, any questions here?
The chat window has been actually pretty lively. I've been fielding a few, but there were a few questions around calibrator temperature. Wally, can you describe the difference between like operating temperature and then when you speak of specs, what it means to have that controlled environment and where to find those numbers?
Yeah, so if you're looking at, I'll talk about our calibrators because those are the ones I know the best. But so our calibrators are generally specified at a temperature of 23 degrees, usually plus or minus 3 degrees, and these are in Celsius. So they're required that you stay within a plus or minus 3 degrees to maintain their performance specification. Outside of that, there's some additional adders you would have to add, you'd have to do to provide to calculate the performance of the calibrator. And again, different calibrators have different spec limits, but our stuff is generally 23 degrees plus or minus 3. Some stuff might be plus or minus 5. But that's the environment that we're expecting the calibrator to be operated within.
Excellent. Thank you, Wally. There's one question that just popped up. What is the RH relative humidity range in which you're recommending that we should do the DMM calibrations?
I don't off the top of my head know what the range is on our calibrators, but that's going to be the device that's probably more sensitive than the multimeter. I want to say it's 70% to 30% relative humidity, but I'm just guessing, and that would be something we'd want to look up specifically at each of the calibrators to make certain that you've got a humidity range that's appropriate.
Thank you, Wally. I would say as well, I think many of you will be looking at doing calibrations either on site, that's becoming popular, especially as COVID turns down a little bit, or in a lab. And in both situations, the specs are really important because depending on the environment you're at, you could have out of tolerances or inaccuracies. The one thing I think, Wally, you'll hit on a little bit later, the power of automation. So everything that we looked at here with the calibration, all the math, all that is, we have software that actually does that for you. And so Wally will touch on that.
That makes it easier. Yeah, for certain. So a couple of things that when you're looking at calibrating a DMM, some level of technical knowledge is certainly helpful. You need to understand a couple of things is what happens if I find, an out of or a test procedure or something, if you do things in the wrong order. Most DMMs, and we'll talk about it, their basic function is volts and everything else is added onto it. So often you're going to want to calibrate volts first. The manufacturer will have a recommendation of the order. What happens if a parameter fails spec? What do you do at that point? Do you adjust it? Do you call the owner of the equipment and tell them that his device was out? What if the instrument requires some troubleshooting even to determine that you've got it working right? So a lot of these things are what I call some technical knowledge, both of the product and of the process. You know, a technician that understands the technology really, really is an asset in the lab. It does help when you're getting to some of those questions. Let's take a simplified look at the block diagram of a digital multimeter. The function of a DMM is to take an analog input, volts, amps, ohms, and that goes into a measurement section. The measurement section analyzes what that input is, digitizes it, provides a value, and sends it to the control section, which is essentially a computer, a control section, and a display. They generally are isolated. The measurement side is isolated from the rest of those subsections. And if you look at calibration, the digital side, the computer side, there is no calibration there. It's either on or off, working or not working, and you don't look at calibration. All of the calibration is really focused on the analog measurement section. When I look at the analog measurement section, you might see something that looks like, a diagram that looks like that. And I said, you generally start out at DC voltage. And there's often variety of different ranges that you have to take a look at and calibrate. Some of those ranges are used by other functions. Some of them are not. So like AC voltage, for example, there is a particular input to the AC voltage, which usually is a resistance that generally in most modern practices uses the 10-volt output to be measured, the 10-volt section. If I look at resistance ranges, there are a variety of different resistance ranges. Those, depending on the magnitude of the resistance that they're measuring, may scale into either 1/10 of a volt, or 10 volt on the DC side. Then there's current ranges, which have a variety of different shunts. Those things generally all get scaled down to one range, and then either will get passed through the DC or the AC section of the meter and out. So the beauty of this is that the DC volts is really the critical section, and generally that's the section that you want to look at first, make certain that that is working and in tolerance, and then you can do the other sections. There is more information that we can provide. There's an app note that provides some information on general test strategies for calibrating DMMs and kind of the rationale for testing. And that's available on our website if you want to dig into that a little bit more deeply. What happens if you have a DMM? Is there a comprehensive philosophy for calibrating all DMMs? And yes, there is. There's DMMs have at least 5 functions, so you need a procedure that looks at least at those, but there are other functions that you'll look at. And there is a published guide that can help provide some of the answers if the manufacturer doesn't provide those by themselves. One of those guides, there are a couple of them, but this is just one that I can point to easily. It's a Euromet, which is an organization out of Europe, the European Association of National Metrology Institutes. They publish several different guidelines. Here is one for calibrating of digital multimeters, and it provides guidelines for calibrating DMMs. I will say it's a good guideline, but it doesn't replace, nor does it supersede manufacturers' recommendations. Manufacturers' recommendations are probably the most detailed and the most correct. They have manufacturers put those guidelines and recommendations together based on intimate knowledge of their design and the way their device operates. This guideline sort of looks at these in generally, but it provides, this document is good. It provides guidance on terminology, some ideas on the procedure, what measurement uncertainty you should look at, and the contents of calibration certificates. What you need to document, and what needs to be documented on the cert. This was updated back in 2015. The previous version, version 2, was from 2011. There have been there were quite a few changes from version 2 to version 3. So if you're still using version 2, I would suggest you take a look at version 3. So what are the sequences that you perform? Depending on how you receive the device, you could actually perform 3 different sequences. One, you could just do a verification only, no adjustments, just noting whether it's in or out of tolerance, pass or fail. There's a third one where you actually, a second one where some people will do an adjustment and then do a post-adjustment calibration as left. A lot of times you'll see that with very new devices. They don't bother to calibrate it when, until they've adjusted it. But some other manufacturers, other people will do that too, because it skips one of the steps potentially. The most common is the third alternative, which is really you collect a set of as found data, you do an adjustment, then you do a post adjustment calibration as left. So that one tends to be the most common and the most useful for most customers. If you look at that CG15's recommended measurements, they actually have 2 different recommendations. If you don't have the manufacturer's manual, again, these would be appropriate to use. Where did my mouse go? There it is. Okay. On the left, you'll see table, right? What's labeled as table 1. These are their recommended measurement points for things that are, 4 3/4 digits or less. So on DC volts, you can look at it. In all ranges, they're going to want you to look at 0, plus 10%, plus or minus 90. In a couple of ranges, they're going to want you to look at additionally the midpoint, the 50% range of the range. But you can look at those for all the different points. For DMMs that are greater resolution, they're requiring, or they're recommending more measurement points. On all ranges, now they're looking at 0, plus 10%, plus 50%, plus or minus 90. And then in some select ranges, 10% of range, 30% of range, 50% of range, 70%, and 90% of range. So a lot more measurement points on a more accurate or a DMM with higher resolution. What needs to be in the certificate when you're done? So on the right here, I showed a first page of one of ours. This happens to not be a DMM, but I just grabbed a cal cert because that first page is all similar. This is a pressure device, but you'll see at the top that we identify generally or specifically what the device is. What's the manufacturer, what's the model, what's the serial number, when was it calibrated, what was the temperature of the calibration, what was the humidity, what was the barometric pressure that we calibrated it in. In here, you also need to identify the procedure. So what procedure was used so that somebody could say, tell me your procedure and I can verify what was done. There needs to be an evidence of traceability, which means the devices that were used to calibrate it are they in calibration, and who calibrated them? I mentioned environmental conditions. We list environmental conditions so you can say this is the condition under which the device was calibrated. Then on subsequent pages, you'll see the measurement results, each measurement function and range, its result, and along with that, this thing called measurement uncertainty for that range. If you want to know more about calibration certificates, that we do have an application note. We changed our certificate format about, I want to say 4-ish, maybe 5 years ago, and we put together an application note that discusses the format change and what we include in our certificates. And that's still a good guideline for looking at what to include in a certificate. Rich, how are we doing for questions?
We're doing good. A question that has come up, you touched on it a little bit, confidence levels, 99, 95. What does that mean, and how does it affect EMM calibration?
That's heading down the rat hole of going away from basic to more advanced, but confidence intervals generally is a statistical measurement of the probability that a measured value is within some level, some band of values. There, if you understand measurement science, there's no way to exactly know the true value. So what we do is we'll say, this value, going back to my DMM, we measured this is supposed to be 5. We could measure it anywhere between 4.993 and 5.007. Say we measured 5.01. There's probably, we'd say there's some confidence or some level of statistics that would say the true value is somewhere in that range. So we need to understand, that's what those confidence levels do. 95% generally means that we're 95% confident that the true value is in their range. If I go to 99%, same statement is 99% confident that the true value is in that range of numbers.
Thank you, Wally. Yeah, so I would actually, there's a lot of statistical type videos on Google as well as an introduction. I think in the future when we do our specifications webinar, we'll focus on that as well.
And I think there's a good seminar on measurement uncertainty that's recorded on our website that if you want to dig into that subject, that might be good material to look at and listen to as well. I think Jeff Gust, our principal metrologist, put together that information.
Thank you, Wally. Great question from the crowd. Here's actually a really good one and a kind of a brain teaser, but very specific to our topic at hand here. So a troubleshooting question, Daniel asked, I ran into a strange issue when calibrating the Fluke 87 multimeter last week. When I sourced voltage to the multimeter, I was receiving back very wild reading and would constantly rise or fall. When applying pressure to the input jacks, my reading stabilized and it was within tolerance. Opened up the meter to lift the solder points in the input jacks, and they all had good connections with no visible breaks. If the solder points were good, could it be possibly just an issue with the board going bad? I just thought it was strange that it was getting the proper reading when applying pressure to the jacks, even though the connections are good.
I would have thought it's interesting. When you get into this, the way you connect the test equipment, you need to pay attention to. It needs to be consistent, reliable. That's one of the reasons if you look at really high-end meters, let me go back a couple of slides. Here we go. Just to bring an example here. Maybe going all the way back. So if you look at these meters, handheld DMM and the bench DMM both have what we call standard banana jack connectors. And you can place a banana plug inside of them, and that's what you're going to make your connection. The laboratory meter also has banana jacks on them, but optionally, it also has a screw down connector for using spades or bare wire. And the reason that's done is you can control the amount of force or the pressure on the connection point. Banana jacks over time, they're spring-loaded devices, and you can actually, over time, that spring will wear out. The other thing that will happen as repeated insertions and removals, you can actually move some of the metal around those banana jack connectors to the point where you might have marginal connections. The other thing you might have is dirt that gets in there and makes connection problems as well. So if you don't have a good solid connection to your device, that's a source of error. And higher end devices tend to compensate for that by providing something that's easier to clean and something that you can provide precise force in terms of by screwing the thing down, a better connection. So I would have thought, just from the way you were describing it to me, that you might have actually just run into it could have been dirt, could have been a bad spring connection on your banana jack, could be a bunch of other things. But that's where I would have gone immediately. Pulling open the board, looking at solder joints, that would have been a secondary look. My first one, and maybe you already looked at the jacks and those sorts of things as well.
Thank you, Wally. In the next coming seminars, we actually have a full webinar on best practices for cable and leads. And we know that that is one of the largest challenges and sources of issues when doing calibrations, especially on higher end calibrations and some certain types of sourcing, resistance, for example. So we will go into that in detail. Please continue, Wally. Thank you.
So let's go through a couple examples here of practical tips and things that you look at for DMMs and how to calibrate them. So number one, I would say, depending upon the device, look at different types of calibrations. So if you've got a lot of DMMs, sometimes just a simple go, no go, or pass fail test is all you need to do. And it's the fastest. It gives you, yep, the device is still working. It's within limits. It's pretty simple. You can take the performance test published for that meter, plug it into your calibrator, and within a couple of seconds, you can say, okay, well, I've got 5 volts coming out of the calibrator. I'm measuring 4.995. I can look at my test limits and, yep, I'm good, done. So again, that's quick and easy. If you've got a large volume of stuff, sure, way to go. But it does leave some unanswered questions if you're looking at more precision devices. So how well was it within spec? What happens if it gets right at that, maybe the lower limit, the 4947? Is it marginal, borderline? Some things that, if you're just doing pass fail, don't often get answered, and in some cases it might be important. I see pass fail acceptable for some applications of handheld DMMs, but as you get into higher performance instruments, it's generally there's usually more information that's needed. Ultimately, the one way to do this would be to document the UUT measurement. So in this case, note the actual measurement and publish it on the report. Enter it on the test record. Then you can easily evaluate each point for pass, marginal, borderline, fail conditions. And again, this is a more complex test because you're now recording values, but it provides more information about the device under test. Here's an issue that happens a lot. Do you normalize the UUT reading? So in this case, this is an example of normalizing it. I take my calibrator and I've adjusted it, the output of the calibrator, such that my meter is reading the value I want it to read, 5 volts, right at that test point. So my calibrator has been adjusted. And over on the other side of the screen, it says the reference was 5, and the error that I'm sourcing is minus 0.1%. So the calibrator actually identifies displays the actual error of the UT, so you can compare it against a spec. So a lot of times specs are written in percent of reading. So here is 0.1% of reading. So it's really convenient to be able to do this for manually operated calibrations. Tip 2, an easy way for using one of our calibrators is to look at whether the calibrator has the appropriate level of specs to do that point. So the calibrator can actually display what its specification is at the value being sourced. So I can look at this 5 volts, 500 hertz, and on a 90-day since calibration, the calibrator is 0.037%, or within a year, it's 0.042%. So I can look at that directly and confirm whether the calibrator is 4 times better than the device I'm calibrating or not. It's really handy to be able to determine whether I have a sufficient calibrator. Tip 3, lots of different issues when I'm calibrating resistance. And there's a lot of inherent 2-wire resistance devices that just the leads themselves cause problems. So if I'm sourcing from a calibrator a resistance, the meter gets to read the resistance that's coming out of the terminal of the calibrator here, plus all of the resistance in the test lead here. So if you're measuring small resistances, the test leads, a couple ohms maybe, or a couple tenths of an ohms, I should say, might be significant in the total overall measurement. There are ways to offset this. And what I'm showing this connection point here, I'm showing the ability of the calibrator to be sourcing resistance, but using another set of test leads to monitor the resistance at the terminal of the DMM. That's what the second test lead does. It actually allows us to determine what's the resistance here, and then feed that back to the calibrator such that it sources a different value to compensate for the test lead resistance. This is typically something you do, say, below 10K ohms. And our calibrators have different ways of providing compensation to either add or remove the offsets associated with connecting to the calibrator when we're doing resistance. Considerations for high current. There's lots of, everyone's current is one of the 5 core functions, and often none of our calibrators produce more than 20 amps. But, and the way we measure, so for example, this current clamp that goes up to 1,000 amps, we actually multiply that current magnetically through coils, and then simulate 1,000 amps. The challenge here is that coil has an impedance, and the calibrator has to be able to drive current through that impedance. And that becomes tricky as we get higher frequencies and higher currents. So the calibrators, generally, you have to worry about when they're operating at high current, are there time limitations? How long that current can be sourced before the calibrator starts overheating? Does the calibrator have enough compliance to be able to drive those coils, that impedance at the current and amplitude or the frequency?
So, hey, Wally, just
yes.
a real quick time check. It's 8:55, so we have 5 more minutes.
Right, and we're pretty close. Good. Understanding compliance and things, this is something you need to look at the spec of the calibrator. And I'm sorry that the spec over on the right is a little bit of an eye chart. But if, for example, I needed to calibrate 1,000 amps, my calibrator needs to supply 20 amps at 50 hertz through a 50 turn coil until it's stable. So concerns I have is inductance. How long does it take both the calibrator and the coil to stabilize? What's the compliance voltage that the coil is going to present to the calibrator? And how long am I going to need to operate this thing? So I highlighted some specifics out of our spec sheet. You know, what is our accuracy here? For currents greater than a certain amount, we need 30 seconds to operate, to stabilize. Once we go above 30 seconds, we have a different floor spec. It's a lower floor spec, it gets better. The other one ends up being is what our maximum compliance is, and how long, and what can we drive through our calibrator. The last tip, and this is automation. A lot of modern practices will drive you towards automating. There are a lot of significant benefits. There are certainly some benefits of being able to perform calibrations quickly and efficiently, boosting productivity. My own personal opinion is that automation, the biggest benefit for automation is doing a uniform procedure every single time that doesn't vary from operator to operator, allowing you to really have consistent results. But that's just, just my personal preference. A common software platform that works over a wide range. A lot of times labs do more than just calibrate digital multimeters. Sometimes they calibrate mechanical dimensional instruments as well. And then managing all of those things into a single database. So somebody can say, you calibrated this thing last year, what was the results? Being able to pull that up and look at it, understand it. And then of course, keeping all of that data secure. These are some charts that talk about productivity increases. Again, automation, depending on how complex the device is, really can add some benefits, like a spectrum analyzer, which is a very complex device, thousands of measurements. You get quite a bit of improvement. Handheld DMMs, there is some improvement, but a lot of the time is operator time in terms of moving the knobs, changing the functions, changing the test leads.
Well, excellent, Wally. Thank you. I just had a few questions that came in here. Okay. We showed the Euromet standard is from Europe. Is there a similar guide from the US?
Yes, there is. NCSL publishes a similar guideline, and ANSI also publishes a guideline. The Euromet I use predominantly because it was it's more it was easier to get to, and it's available for free.
And then the last question here is, what classes or courses do you suggest for someone who is new to calibration?
I'm going to point you, I mean, if you're interested in calibration, I think probably the best organization to look for further training is the National Council of Standards Laboratories, NCSL. They do have training materials, training courses, and they have a list of third-party training consultants that you could use. That's one of the first places I would look. If you're in the United States. Outside of the United States, I'd look at the Euromet organization in Europe. There's an organization also that's international. It's called IMECO, IMEKO. And in Asia, there's a group called APMP, the Asia Pacific Metrology Program, APMP. They also have training materials or recommendations for training.
Excellent. Well, it is 9 o'clock here, so we're right on time. Wally, I wanted to say thank you for your time and expertise. Always a pleasure to have you here helping us out. And so everybody on the webinar, thank you for attending. We will be sending up a follow-on email, and shortly after that, we will send out the recording to this. It may take a couple days, but we will do that. But we look forward to your feedback. We also, if you have any questions, feel free to reach out, and we're glad to serve you. Thank you.
Thank you, guys.